Okay, 8.4. This is a fun little application of scale factors. If you're making diagrams bigger or smaller, it's interesting to look at how it's actually going to affect the area. And there's a very predictable way to do it, but it's not obvious at the beginning. But at the end of this lesson, it'll be very, very obvious. So let's start with, you should pause this and see how many of these formulas you have memorized. You do need to have all of these memorized for this unit. So there's a bit of memorization. It's a geometry unit. So pause this. I'm going to start it again in 10 seconds. Okay, I'm going to go in a different order. I'm going to start with the easiest one, which is a square. The formula for the area, this is always A equals. Sometimes we use subscript to say what shape it is. This one is going to be S times itself, so just S squared. Area of a rectangle is length times width. So those are the two easiest ones. Next is probably a triangle. Triangle, it's base times height, but that would give you the area of the entire rectangle. And triangle is exactly half that. So base times height, cut in half. Parallelogram. This one is just a rectangle that's been pushed over sideways. So if you like to, you want to think of it like a rectangle before it got pushed over. So you want to treat it like that's its length. We call it the base though. And you want to push it back so it's straight up and down. So it makes 90-degree angles. And that's what we're going to call the height. The height is not this diagonal. We do not care about that one. It has to be the full rectangle of the shape. So this one is just base times height though. Trapezoid, this one's far less common, so not too worried if you don't have it memorized, but it's actually kind of easy to remember once you know what you're doing. Basically what you want to do is we're looking for the rectangle, which is halfway between A and B. If we cut this like in half this way, and turn that into a rectangle, this little sliver down here that we have extra should be the same size as this little sliver up here that we're missing. And same thing on that side. So if we averaged the lengths of A and B, that should just make a rectangle that fits with H. And multiply those two numbers. And how do you average something? You add them together and divide it by 2. So if you do that, then all you have to do is multiply that number times H. So the average of A and B times H is that one. And then this one is really just a memorization, but it kind of rolls off the tongue. It's pi r squared. Okay, so let's get right into it. We're going to fill in this chart and we're going to look for a relationship between how the size of the shape is changing compared to the area. So it says start off with a square that's 1 by 1. What is the area of that? Well, it should be 1 times 1. It should be 1. We'll leave off units for this one. It doesn't say units. Now it wants you to go on to 2 by 2. So if we doubled the size of it, or if we multiplied it by a scale factor, does that double the area? Seems like it should. But this time it's going to be 2 times 2. It's actually going to equal 4. What if it was, should we go to 3 by 3? Yeah, let's do 3 by 3. That one's going to be 9. Just length times width, or length times itself. 4 by 4. 5 by 5. 6 by 6. And 7 by 7. Let's try a couple more. So 4 by 4 is 16. 5 by 5 is going to be 25. 6 by 6 is 36, and 7 by 7 is 49. It's just our squareds numbers, all of our special purple numbers up there. What do you think the area of the 10th square in this chart will be? Well, that looks like it's going to be 10 by 10. It looks like it's going to be about 100. And it will be 100. We're good with that. But let's try some deeper analysis on the next page. When the dimensions are doubled, how did the area change? So if we doubled the dimensions, did the area double? No, it looks like it was either add 3 or times 4. Not really sure. Let's try another one. To double it, we go from 2 to 4. And this time it went from 4 to 16. So it is indeed quadrupling it. When the area is doubled, when the dimensions are doubled, the area is quadrupled. When the dimensions are tripled, how did the area change? So tripling it, going from 1 to 3. This time it was times 9. Let's try another one. From 2, let's triple that. That should be 6. Goes 4 to 36. How much bigger is that? Well, I do 36 divided by 4. That is 9 times bigger as well. So when you triple the dimensions, you're actually timesing it by 9. If the dimensions are quadrupled, how much is it going to be? Well, 1 to 4 is 1 to 16. Looks like 16 times bigger. That one was times 4, times 9, times 16. Is there a pattern to how the square grows and its area? What is the pattern? Fill in the rest of the chart. So what's actually going on here? 4 becomes 16, 3 becomes 9, 2 becomes 4. How do we get from the one number to the other number? It should kind of pop out at you. What we're doing is we're squaring it. We'll call it the factor. So the amount we're multiplying the lengths by, we're squaring that number to get to the new area. That works for squares. Let's see if it works for other shapes. So let's see if we can find a pattern with other shapes. Let's start with a rectangle 3 by 4. So we have a rectangle 3 by 4. Let's try doubling it. If we double it, it's going to go 6 by 8. Okay, what was the area in the first one? Well, that should be 12. What's the area in the new one? It's going to be 8 times 6, which is 48. Now, how did we get from 12 to 48? We timesed it by 4. So it was 2 times bigger, but the area is actually 4 times bigger. Or whatever the scale factor is squared. So if I wanted to triple this size, to triple it, I would go to 9 and 4, 8, 12. And without multiplying these, I can tell you what's going to be in here. Because these became 3 times bigger, the area is going to be the area times 3 squared. You square whatever the new size is. It's a little bit of a confusing formula. So basically the area times 9. So 12 times 9 is 108. And is that true? 12 times 9 is indeed 108. Yeah. So in summary, when the dimensions of a shape are multiplied by a factor of k, so if you're making the size k times bigger, which is what we're doing every time we have a scale diagram, the area of the shape is going to be multiplied by k squared. Whatever k squared is, you have to multiply by that number to get the new area. So there is a relationship, but it's not an obvious one, and it's not the same number. This is not 2 times bigger, and this is not 3 times bigger. That one's 2 squared times bigger, and this one's 3 squared times bigger. Okay, so let's try that in action. What would be the area of this image after it's enlarged by a scale factor of 3? So we need to know what the area is right now. This is actually going to take a little bit of work. We need to turn it into some shapes. We have a triangle there. We have a rectangle there. We have a rectangle there. We have a square there, and we have 3 extra squares. So let's find out what all these different shapes are. Well, this is 2 times 1, 2, 3, 4, 5, 6, 7, 8. 2 times 8, that's 16 squares. 3 times 4 is 12. 3 times 3 is 9. That shape up there has exactly 3 squares. And this guy, 1, 2, 3, 4 times 2 is 8 cut in half. That's why we need the formulas. That guy's exactly 4. Base times height divided by 2. So the area right now is the sum of all those: 20, 32, 41, 44. And you guys can do that in your head as well, I'm sure. No calculator required for you guys. So now, let's pretend this is 1/3 of its real life size. So we want to know how much of an area this is in real life then. Or if you had to make this 3 times bigger, what would the area actually be? So it is not 3 times this area. The area does not grow by 3. What you do is the area in real life, we'll call it, is going to be our 44 times our k value squared, because area is the second dimension. That's the easy way to memorize this. So it's times the scale factor in the second dimension, so it has to be squared. And that number should be quite large, actually. So 9 times 44 is 396 squares in real life. Hard to believe, right? So basically we're taking this bottom is, we said 8. We're turning 8 into 16 into 24. So that bottom's going to be 24 across. The top, instead of being 5, is going to be 15 up. So it's only 3 times wider, 3 times taller, but the whole area actually has 9 times the amount of squares now. That's how that works. Okay, let's try this next one. Determine the scale factor relating this pair of similar shapes. So we know the area difference, we don't know the scale factor of it this time. So first of all, what's the actual ratio of the areas? So we're going to do 24.5 divided by 12.5. That's 1.96. So it is 1.96 times bigger, is basically the area is. The area is 1.96 times bigger. We want to know what the k value is. Now the k value is equal to the area's k value squared. So this is dimensions, this is area. So whatever this number was, that's actually the squared version of the original. So we could say k that we're looking for is equal to 1.96. But that's the whole squared version. So what we're actually looking for is we have to square root it. Sorry, we square root both. This is confusing. Sorry, I'm not explaining this very well, but the 1.96 is the squared version, so if we square root it, we get back to the original k. That's what we're trying to do in this case. So if you had the dimensions one like we did in this one, which was 3, we have to square it to get the multiplication. Sorry. In this one, the k value for the original function was 3. So in the area, it became 9. You had to square it. This time you have the area, so you have to square root it to get back to the original k. Probably shouldn't call this k. We'll call this ka, the scale factor of the area. So the square root of 1.96 is 1.4. So the actual scale factor is 1.4. In this one. Hopefully that makes sense. It has to be a smaller number. The amount you're growing by is always bigger in the area if you're growing. Okay, last 2 questions, I guess, sorry. My computer screen is currently being projected onto the smartboard. It isn't, but let's pretend it is. Dimensions of the computer screen in this scenario is 10 by 16. So we have a little computer screen that is, I assume, wider than it is tall, 16 by 10. And the area of the smartboard is much bigger. It's 2,829. Okay. If the image on my smartboard is similar to the image on the computer, so if it's the exact same dimensions, exact same kind of shape, that's what similar means. Similar is same shape. Different size. What's the scale factor used? How much bigger is something? If I had a line on here, how much bigger would it be when it comes to this size? So how can we find that one out? We need to know something similar. We don't know how to break this down into its dimensions, but we can turn this into its area. So 10 times 16 is 160. Okay, now how much is the area being multiplied by? To find that, we take 2,829 and we divide it by 160 to find out how much you multiplied by. So diagram versus real life, or however you want to think about that. I always put the big one on top, pretty much. It does work a lot of different ways, the k value. So it's hard to give you absolute rules. In this case, I'm going to say it's an enlargement, and therefore the big number on top. 2829 divided by 160 is 17.68. So the area has grown by a factor of 17.68. So the actual scale factor is going to be the square root of that. You have to go backwards, shrink that number back down to see the scale factor, which means the scale factor should be 4.2. So, in theory, the screen is actually 4.2 times bigger, in which case this should be 42, and 16 times 4.2. This should be 67.2. If you use that scale factor of 4.2. And let's double check our answer. Let's say we're not terribly confident we did all those numbers right. It's a bit confusing. We should be able to multiply these two things together to get back to the original area. So let's actually check that. And I get 2,822.4. A little bit off because we've been rounding. I rounded this number and I rounded this number, and I even rounded these numbers. So we did some rounding, but it's generally the same number. We didn't get something like 10,000. We didn't get something like 65. It's not way off. We didn't do any wrong calculations. Oh, and that's actually what we have to do here. What are the dimensions of the smartboard? So you multiply these by our actual scale factor, 4.2. The length is 67.2. Do we have units? Inches. And the width is 42 inches. Good. I think these shouldn't be too much trouble. I think you can usually common sense your way to an answer even if you get terribly stuck. But do try questions. like I said, again, this is a lot of questions. I expect you to do at least half of them. So pick questions that you think are going to challenge you and improve your understanding of this unit. Okay, good luck.